Hi there, welcome to lecture 22 of Fox, where we're going to begin the next journey in this course, the next part of this course. So for the last 20 or so lectures, we have been covering intensely discrete math. And where are we going next? Okay, perhaps the most important application of discrete math in the 20th and 21st centuries, the digital computer. So we are going to build and analyze a model of the digital computer. We're going to study what are the capabilities of computing. Okay. And we're going to begin this study in what might look like an unusual way. We're going to start by talking about infinity. Infinity? What does that have to do with computing? A computer is this finite object that's sitting in front of us doing all kinds of fancy things. Why do we need to study infinity? Okay. And so, let me address that a little bit, but it'll become clear through the course of this lecture how infinity is going to come back and have a lot to say about the capabilities of computing. Okay. Now, if someone were to ask, well, what is computing? Okay, so, the first thing that might come to mind is, it's the study of the digital computer. But it was Dijkstra who said, to say that computing is about the study of digital computers is like saying that astronomy is about the study of telescopes. No way. Computing is not about the study of the digital computer. The digital computer is just how today we choose to implement some of the things that we would like to do and things that we call computing. Okay. But computing is the study of algorithms. But what's an algorithm? Well, we don't have a definition yet, but Stephen Klein, gave a very beautiful definition of what is an algorithm in just one sentence. He said, an algorithm is a finite answer to infinitely many questions. How beautiful is that? Okay, so let's think about that a little. Think about a sorting algorithm. A sorting algorithm. So you have a sorting algorithm. You implement it as a program on a computer, but what does it do? It takes as input a list and produces a sorted version of the list. So there's an input and then there's the output. And you can think of the output as the answer. Okay? And this algorithm has to produce the correct answer for infinitely many inputs, because there are infinitely many different input lists that we could create. So an algorithm is a finite answer to infinitely many questions. And there you already see a hint of how infinity plays a role. How can we sort of build finite answers to infinitely many questions? So infinity is going to come in and have some role to play. Okay, so we're going to begin this journey, the study of computing, the theory of computing. And essentially we're going to follow the path that was laid for us by a famous guy by the name of Alan Turing. This guy is that famous. Okay, we have named the pinnacle of this sport after him, the Turing Award. If you can win the Turing Award, you're done. You don't need this book. You don't need this course. You're set for life. Okay? So go try to win the Turing Award. That's the pinnacle of the sport. But that tells you something about what this guy has contributed to the field. Okay? He basically gave us the theory of computing. He gave us a lot more. Okay? He helped England win the war against the Germans with his code-breaking abilities. He gave us the Turing test, which defines the intelligence in AI. Okay, so it's a test for intelligence. Okay, so he gave us so much. He gave society, he gave humanity so much. It turns out that his life was a tragedy. And you can read more about it in the text. You can read about it on the internet. He was burglarized. The police, in investigating the burglary, found out that he was gay. And strangely, at that time, that was not allowed. Okay, people were so closed-minded. They were not tolerant of other people's ways of life, other people's views. And so instead of, prosecuting and arresting the burglar, they prosecuted and arrested Turing, and he's the one who was punished. Okay? And, he went into depression and so on and so forth. Ultimately, he committed suicide. What a tragedy to lose such a brilliant mind at such a young age. Okay? It just shows that there's a lot to be gained by being tolerant. But anyway, you can read more about that on the internet, in the text. Okay? We are going to begin our study of Turing's theory, our study of the digital computer, our study of what is computing. Okay, now, before we get going, let me just give you a quick summary of the last 20 or so lectures. Okay, we studied discrete math, and it was really a short stroll through discrete math. Okay, we talked about precise statements and proof. Okay, and then we introduced this all-powerful proof technique, induction, very powerful for proving for all. And then we talked about, and induction plays a role everywhere in discrete math. We talked about recursively defined structures. We talked about sums and asymptotics and the relevance to computer science, number theory and cryptography. Graphs as a fundamental way to represent relationships. All kinds of problems we like to solve can be represented as graphs. We talked about counting and how important counting is to basic analysis of algorithms, and how important, what a beautiful subject counting is in general. And in fact, counting is going to play a role in today's lecture. Okay, Okay, and then we talked about probability. It's a relatively new injection into computer science, but I'll just give you some quick pointers to why we study probability. So real-world algorithms involve randomness and uncertainty. The world is, random. The world outcomes in the world are sort of uncertain. Inputs arrive in a random order. And nowadays, we have what are called randomized algorithms. For example, primality testing. Machine learning is inherently a randomized algorithm, and that's all the rage today. Routing, conflict resolution, these are all randomized algorithms. What does that mean? It means that those algorithms don't go unless we inject randomness into the algorithm. So probability is playing two roles in computer science today. Probability is the way we analyze the behavior of our algorithms in the real world, because the real world has randomness. And also, we inject randomness into algorithms, and so we need probability to analyze those algorithms. So probability is so fundamental. Okay? And then we talked about, once we've understood that probability is fundamental, and once we've understood the basic infrastructure of probability, you do a complex experiment, it has an outcome, and then you measure something, and then we summarize the entire experiment by the expected value, which tells you, in some sense, on average what happens, and then the variance, which tells you how good that expected value is. How good is that summary of the experiment? Okay, so that's the short stroll through discrete math. Okay? And it's a lot of material, and it now is, might be a good idea to go and reread the material, redo the exercises, redo the pop quizzes, and so on and so forth. It's worth mastering discrete math, especially since it's going to be fundamentally the core of the next part of this course, which is the digital computer. And what has been more impactful than the digital computer? Well, you can go through history and find a few things that have, but certainly the digital computer is one of the most important arrivals into society, at least in modern society. Okay, so let's begin, and we're beginning, I told you, in what might look like an unusual way. We're going to start by talking about infinity. Okay? And infinity, was not understood by many of the great mathematicians, and it was not until Cantor came along that we had some grasp of infinity. And what was his ingenious idea? So he had to really put something ingenious in, because all the greats, Euclid, Gauss, Newton, nobody, everyone feared infinity. Cantor took it head on. Okay? And what was his great insight? So we don't understand what infinity is. Okay? What is it? This is an infinite object. This is this thing we can't comprehend, this thing we can't visualize. Okay? But Cantor said, well, you have two things. You don't understand them, but that doesn't mean you cannot compare them. That was his great insight. He said you don't need to understand two things in order to be able to compare them. Okay? And so we're going to follow in Cantor's footsteps today and in discussing infinity. Okay? And fundamental to the discussion of infinity is that we will never be able to really comprehend infinity. So you have this set that's infinite, and this set that's infinite. We have no idea what that is, but we might be able to compare these two sets and say something about, their relative nature. That is the insight that Cantor brought. Okay? So we're going to talk about infinity. Okay, we're going to talk about concepts like what's countable and what's uncountable, and then we're going to have to address, because we're starting in such a non-traditional way, we're going to have to address why does infinity have anything to do with computing? So what is the relevance of infinity to computing? Okay, so let's begin. And we're going to start by the concept of comparing the sizes of sets. Let's go to the board. Cantor realized that we cannot count infinite sets. They're just too large. We can't count up to infinity. But his ingenious idea was to sort of make this leap that maybe we don't need to count, maybe we just need to compare. Okay. Now let me show you the power of comparing. As a 1-year-old, you don't know how many fingers you have on your right hand because you don't know how to count. But you do know that your right and left hands have the same number of fingers. How? Well, you can put them in correspondence. See? And once you put the fingers in correspondence with each other, this can only be done if you have the same number of fingers in both hands. Okay, so that's the power of comparing. You can figure out that, two sets have the same size, one is smaller or maybe one is larger by comparing. Okay. Now, this notion of correspondence, putting the fingers into correspondence, is related to how we map one set onto another set. So let's sort of define, mappings and show that, by looking at various types of mappings, we can decide whether or not a set is smaller or larger than another set, okay? And maybe even equals. Okay. So here are 4 scenarios. Okay. Well, this is just a playground, 3 real scenarios. So in this scenario, it's clear that, the size of A is less equal to the size of B. In this scenario, it's clear that, the size of A is bigger than the size of B. Here, the size of A equals the size of B. Okay. And let's think about, some kinds of functions that map a domain A to a range B. So let's play around here in our little playground. Okay. So let me show you an example of a function. Okay. So here, in order to represent a function from A to B, I can use arrows to map the elements of A to elements of B. Okay, so here. Okay, good. So is there a problem here? So pause the video for a couple of seconds and figure out whether there are any problems with how I've defined a function. Okay, now if you're coming back just for the ride, there are two problems with this function. The first is that a function must be well defined for all elements of your domain. In other words, there should be arrows going out of every element of A. So what about this guy? Where does he map? Okay, we don't know. So this is not a well-defined function. So if I add an arrow, now it looks like maybe it's a well-defined function. Still no, because a function must unambiguously map an element of the domain to an element of the range. So here, where does this guy map? Okay, and we see that, it can either go here or here. Not allowed. Okay, so you have to get rid of one of these arrows. You cannot have this kind of ambiguity in a well-defined function. So now I have a well-defined function. Now we don't have a problem anymore. Okay, every element of the domain is mapped, and every element of the domain is mapped uniquely. You don't have any doubts as to where any element is mapped. Okay, this is a well-defined function. Now, it's a well-defined function, but it still has a property that I would like to exclude. Okay, and what's that property? Well, let's look at these 2 points. They're different points, but they map to the same value. Not allowed. I don't want to allow that. And okay, those functions which do not allow 2 different points to map to the same point are called one-to-one. Okay, so let me show you an example of a one-to-one function. Okay, so here, now I'm not allowed to go from here to the same value. So, something like that. There, one-to-one. Now what do we see? What we see is that every element of the domain is mapped to some element of the range. Okay, 2 different elements of the domain are mapped to 2 different elements in the range. So that's what the one-to-one means. Here we had 2-to-1. Okay, here 1-to-1 means that one maps to one and a second one cannot map there. But observe that this is a well-defined function, even though we don't use the whole of B. For example, we don't use that point. Now, here's a situation where the size of A is larger than the size of B. Okay? And we can say, well, let's try to construct a one-to-one function. Okay, so maybe we'll map this guy here. 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 Okay, but where does this guy map? Okay, he has to map to one of these, and then the moment we pick whichever one this guy maps to, that's going to make 2 map to the same one. For example, if we map here, now it's a 2-to-1. So this is not a one-to-one. In fact, okay, by the pigeonhole principle, if you're mapping these elements in A to elements in B, okay, and there are more elements in A, then by the pigeonhole principle, at least 2 of these elements will have to get mapped to one of the elements in B. So you cannot have a one-to-one function. There's no one-to-one possible. Okay. Now, let me show you the situation with when the size of A equals the size of B. So, let's construct maybe a one-to-one function. Okay, what you will observe is that not only is this one-to-one going from A to B, but it's also one-to-one going from B to A. Okay, and that's possible. Okay, so if there's a one-to-one function going from A to B, it means that the size of A has to be less than or equal to the size of B. Because if the size of A is greater than the size of B, one-to-one is not possible. If there's a one-to-one going from B to A, it means that the size of B must be less equal to the size of A. Okay, so if A is less equal to the size of B and B is less equal to the size of A, that means A must be equal to B. Okay, and here we have 1-to-1 from A to B and from B to A. Okay, sometimes we say that this one-to-one function from A to B, this function from A to B is both one-to-one and onto, okay, or invertible. There are many equivalent ways to characterize this situation. This is an example of the correspondence that we set up between the fingers. This is called a bijection. Okay, so it's one-to-one from A to B, one-to-one from B to A, bijection. That can only be done if the sizes of the sets are equal. Okay, so what we observe, okay, is the following, and now we'll state it as a definition. Okay, if the size of A is less equal to the size of B, less equal to the size of B, if there is a 1-to-1 function from A to B. And we sometimes write A injectively maps, injectively maps, I-N-J, injectively maps to B. If the size of A is greater than the size of B, okay, that means there is no 1-to-1 function from A to B. Okay? And we see that the size of A is equal to the size of B if there's a 1-to-1 function from A to B, so A injectively maps to B, and B injectively maps to A. And together, this means that A bijectively maps to B. Okay. Now, it turns out that all these are easy to prove when you're dealing with finite sets. Okay. And the leap that Cantor made is that we're going to use this same function-based approach to comparing the sizes of a set when it comes to comparing the sizes of infinite sets. Except that with infinite sets, you can't really talk about the size. Size only makes sense with finite sets. Okay, and with infinite sets, we can only compare whatever the notion of size is, and we call that the cardinality. Okay, so definition. We say that the cardinality of A, which for finite sets is the size, the cardinality of A is less equal to the cardinality of B if you can find a bijection from A to B. Okay. So how do you prove? To prove the size of A or the cardinality of A is less equal to the cardinality of B, you just find a 1-to-1, i.e. injection from A to B. Now this means a few things. First of all, you must find a valid function. So you must show that your function is a valid function from A to B. And then you have to prove that it is an injection. Okay? And what do we mean by injection? It means that two elements of A cannot map to the same element of B. Okay? And we'll see some examples of that. Okay. To prove that the size of A is greater than the size of B, this is tough. You have to show that there is no such injection. You have to show there is no 1-to-1. There is no injection from A to B. So you have to show that you're in this situation. Okay? So if the size of A is greater than the size of B, there is no injection from A to B. If there were, then the size of A is less equal to the size of B. To show that there is no injection requires a sophisticated argument. Like here we use the pigeonhole. Why? Because you have to show that there's no possible way to construct an injection. Showing that the size is less equal to B is much easier. You just have to you have to show existence. You have to give an example of such an injection. Okay? And if the size of A is less equal to the size of B, okay, if the size of A is less equal to the size of B, that means there's an injection from A to B. So A injectively maps to B. Okay, and the size of B is less equal to the size of A. Okay, so A is less equal to B. Okay, cardinality of A less equal to cardinality of B. Cardinality of B less equal to cardinality of A. What does this mean? This means that B injectively maps to A. So there's a 1-to-1 from B to A. Okay, well then these together, so cardinality of A less equal to cardinality of B, B less equal to A, these together implies that the cardinalities are the same. Okay, now it turns out that for finite sets, this is easy to prove, and you can see the book for an exercise. For infinite sets, okay, it turns out that this is non-trivial to prove. In fact, this is called the Cantor-Bernstein theorem. It's non-trivial to prove. Okay, but it has been proved. Basically, what has to be proved here? You have to show that if I give you an injection from a set A to B, okay, and I also give you an injection from a set B to A, it's possible to construct a bijection from A to B, a 1-to-1 correspondence, a correspondence like this. a map that's both injective and what's called onto. So it uses all of A and all of B. Okay. Now, so the way we're going to sort of approach comparing sets is using this mapping-based approach. So if you give me two sets, and now the two sets can be infinite or finite, I can compare their sizes, their cardinalities, okay, if I can find an injection from one to the other. If I cannot find an injection from one to the other, that means that means one of them, that the one that I cannot find an injection from is larger. And if I can find an injection from one to the other and from the other back to the one, then the sets have the same cardinality. Okay. So let's do some examples. Okay, so examples. And we'll start with a simple example. Okay. There is a bijection from the finite set A1, A2, A3 up to AN. You can bijectively map to the set 1, 2, 3 up to n. Okay. In fact, that's what it means for a set to have size n, if there's a bijection from the set to this finite set 1 to n. Okay. And what's the bijection? Let me show you the bijection. It's just A1 maps to 1, A2 maps to 2, A3 maps to 3, and so on. AN maps to n. Okay, so that's a bijection. It's an example of a bijection. That means that these two sets are the same. Well, it's kind of obvious, but I'm just showing you in terms of a bijection. Okay. Let us now consider a much more complicated set, okay, which is the natural numbers. The natural numbers. Well, for us, it's not so much complicated. We took it for granted, but now we're studying infinity, so we're really trying to get into the depths of this set, the natural numbers. Okay, so the natural numbers is equal to 1, 2, 3, 4, up to, and so on. Okay, well, this is an infinite set. Okay, so we are going to be interested primarily when studying infinity in comparing the sizes of sets to the natural numbers. Okay, so the cardinality of the sets to the cardinality of the natural numbers. So we are going to compare. We are now going to compare sets to n. Okay, so let's start with any finite set. So let's start with any finite set. A1, A2, up to AN. Okay. So, what is the cardinality? Oh, intuitively, you can think of size, but for the moment, let's call it cardinality. Okay, what is the cardinality of this set in comparison to the cardinality of the natural numbers? And in this case, we can show that this is less than or equal to the cardinality of the natural numbers. Okay, so now why? Okay. Well, in order to prove it, we have to find a one-to-one function from this set to this set. Okay. So here are the natural numbers. The natural numbers are 1, 2, 3, 4, 5, 6, 7, 8, and so on. Here's my set A1, A2, A3, A4, A5, and so on. Let's say up to AN. Okay. And I'm going to find a mapping. Here's the mapping. 1, 2, 3, 4, 5, 6, and so on, all the way to n. Dot, 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 n here. Okay, dot, dot, dot. Okay. And now you look at this and say, well, is this an injection? Is this a one-to-one mapping? Well, yes, it's well-defined, so it maps each of my members of A, okay, if you call this set A, to a valid natural number. One of these, no two of these go to the same natural number, but you might complain, but look, you haven't used most of n. Okay, so that's the interesting part of an injection. An injection does not have to use the whole of the set B. Okay, it only has to make sure to show you where to map every element of A. It doesn't have to use the whole set B. Okay, so let's look at a typical injection, okay, from some set A to the natural numbers. So a typical injection, i.e. 1 to 1, from A to the natural number. So what does A look like? And now we'll allow even A to be infinite if we want. In this case, it was finite. Okay? So so here's A. Maybe it's a circle, then a square, then a cross, then a dagger, or whatever, arrow, then, a box with a cross, and a squiggly, and a dollar, and a star, and so on. So that's A. Okay. What are the natural numbers? The natural numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on. Okay. So a typical injection from A to the natural numbers would look something like this. So, you've got to tell me, where does this circle map? Okay, maybe it maps here. Okay, now if it's an injection, nothing else can map here. That's the only concern. Okay, so where does this square map? Oh, maybe the square maps here. Okay. And where does this plus map? Oh, the plus maps here. And what about this guy? This guy maps here. And what about this guy? This guy maps here. What about this guy? This guy maps here. Okay, what about this guy? This guy maps here. And this guy maps here. Okay? So, what you will observe is that I'm not skipping over any elements of A. So in this injection, it has to be a valid function. So you have to tell me where every element of A maps. But you can skip over elements of N. Okay, so here, see, I've skipped over. Skipped over. So I'm not using all the elements of N. Okay. This is what a typical injection from a set to the natural numbers might look like. Okay. You have to use all of A, not necessarily use all of N. Okay? And if you can find such an injection from any set to N, it means that the cardinality of this set is smaller than or equal to the cardinality of N. This is N. Okay? So we are going to be interested in which sets have a cardinality smaller than N, which sets have a cardinality that's equal to N, and which sets have a cardinality that's strictly larger than N. For the moment, let's talk about the sets that have a cardinality that's less than or equal to the cardinality of N. Okay? And that brings us to what we call countable sets. Countable. Okay. So, definition. A set A is countable. Basically, it means smaller than N. But we have to take smaller than with a grain of salt because we don't really know what smaller than means when we talk about infinite sets. We know how to compare with injections. So a set is countable if its cardinality is less than or equal to the cardinality of the natural numbers. And we can loosely say if it is, if it's not larger than the natural numbers. Okay. What does this mean? It means that A injectively maps to N. That's all it means. So you can show that a set is smaller than the natural numbers if you can find an injection, a one-to-one mapping from A to N. What does a one-to-one mapping look like? It must use all of A. It's allowed to skip values of N. Okay. But if once you use one of the values of N, you cannot use it again for some other member of A. Okay. That's the definition of an injection. So what we have shown here is that any finite set possesses such an injection. It's just a trivial injection. You just map the first element to 1, the second to 2, and so on. Okay, so any finite set has size at most, has cardinality at most, the cardinality of N. So any finite set is smaller than the natural numbers. Well, that's intuitive. Okay. So, 1. Any finite set is countable. 2. Exercise. Prove that if a set A is a subset of a set B, then the cardinality of A is less equal to the cardinality of B. It's all very intuitive, right? We already knew that any finite set is smaller than the natural numbers because the natural numbers is infinite, whatever that means. Okay? If a set is a subset of another set, then the cardinality is at most the cardinality of the other set. Okay? Now, you might think, well, how do I prove this? You have to find an injection. So now it's a very formal process. You have to find an injection from A to B. Okay? But in this case, if A is a subset of B, finding that injection is very easy. You map any element of A to itself in B. And how do we know that that element exists? Because A is a subset of B. Now, you should sit down and flesh through that proof. But intuitively, it should be clear that if you're a subset of another set, your cardinality, or in this intuitive size, is less than or equal to the size of B. But we're no longer talking about sizes. We call it cardinality. And you'll see why very shortly. So now, okay, I'm going to define 3 sets. I'm going to define the natural numbers plus 0, n0. Well, I'll define actually 4 sets. So n0. This is the set of natural numbers plus 0. So this is 0, 1, 2, 3, 4, and so on. Which is n plus union 0. Okay. Well, it's clear that n is a subset of n0. Okay, so this means that the size of the cardinality of n is less than or equal to the cardinality of n0. Okay, this we just proved as an exercise. Okay, and intuitive. This is n is a subset of this guy. Okay, so, but what is the cardinality of n0? So here, obviously, the cardinality of n0 should equal the cardinality of n, whatever that is. We don't know what it is. It's this bizarre quantity we call infinity. So it should equal the cardinality of n plus 1. That's intuitive. You're adding one element, right? And if cardinality is supposed to represent size, then, okay, that should be, what we expect. We've added an element, so the cardinality should go up by 1. Okay. 4. Let's consider the even numbers, okay, which is the positive even numbers to make things easy. So this is the set 2, 4, 6, 8, and so on. Okay. Well, the even numbers is exactly the natural numbers minus the integers, minus the odd integers, 1, 3, 5, and so on. So there are half as many even numbers as, natural numbers, because you've removed every other one. 1 is missing, 3 is missing, and so on. So, obviously, the size, the cardinality of the even numbers should equal 1/2 the cardinality of n. Okay. Let's consider another set, 4. Okay. Let's consider the integers, okay, which is, 0, plus or minus 1, plus or minus 2, and so on. Okay, well, let's think about this in terms of the natural numbers. Well, it has all the natural numbers twice. Once with, 1, 2, 3, 4, and then once with minus 1, 2, 3, 4. So it's got all the natural numbers twice plus 0. So, it seems obvious that the cardinality of the integers is equal to twice the natural numbers plus the extra 0. Okay. And let's look at one more set. Okay. So in all these cases, we are expecting the various cardinalities of these sets to be approximately, to be somehow linearly related to the cardinality of the natural numbers. So in this case, it's strictly bigger than the cardinality of the natural numbers. In this case, it's strictly less than the cardinality of the natural numbers. In this case, it's strictly bigger than the cardinality of the natural numbers. And let's consider one more set, which is the rational numbers. Okay. This is a big set. Okay, what is it? Remember what it was? It was, z over n, where z is an integer and n is a natural number. Okay, and so from our counting days, z can take on, one of cardinality of z different choices, and n can take on one of cardinality of n different choices. So we might expect that the cardinality of q, obviously, so the cardinality of q should be equal to the cardinality of Z, product rule, times the cardinality of N. Okay. So this is what we expect. Okay. So now let's come back and use Cantor's approach to comparing sets. So let's compare each of these sets to the natural numbers and see if we can verify our intuition. And we're going to use Cantor's approach, which says when comparing to the natural numbers, see if you can find an injection. If you can find an injection, then it's less than or equal to. Okay. If you cannot find an injection, if there is no injection, then it's greater than. Okay. So in all of these cases, in 3, 4, this is 5, and 6. Okay. I should not be able to find an injection from these corresponding sets. From 3, 5, and 6. I should not be able to find an injection from those sets to the natural numbers because we are expecting them to be bigger. In fact, in this case, it's much bigger. This is much bigger. It's infinitely bigger. It's infinity times the cardinality of the natural numbers. So this is much bigger than the cardinality of the natural numbers. Okay, so let's erase and come back and compare these sets formally with the natural numbers using the concept of injection. Okay, let's compare each of these sets with the natural numbers using Cantor's method of injection. Okay, we'll go through N0 slowly. We'll quickly do E and Z. Okay, and then we'll see what's going on with the rational numbers. Okay, so N0. Well, it's clear that N, the natural numbers, is a subset of N0. So this means that, the cardinality of N is less equal to the cardinality of N0. Okay. Now, I'm going to prove that the cardinality of N0 is less equal to the cardinality of N. Okay. And together, so N is less equal to N0, N0 is less equal to N. So together, this means that the cardinality of N0 is equal to the cardinality of N. Oh, that's a blow. Because didn't we just argue without, any ambiguity, without any reservation, that the cardinality of N0 is the cardinality of N plus 1, which is strictly greater than N? Because look, N0 has strictly more elements than N. How is it possible that their cardinalities can be the same? And so this is the first confrontation of intuition with infinity. Okay? And intuition loses. And so this is where we have to get rid of the notion that cardinality is size. Okay? It's not size. If you had a finite set and you added an element, its size increases by 1. But if you have an infinite set and you add an element, its size doesn't increase. Okay? That's what this shows. Mind-blowing. Mind-blowing. Okay, so let's see why. So I'm going to show this. Okay, and in order to show this, I'm going to demonstrate a one-to-one function, an injection from N0 to N. So here is a one-to-one function from N0 to N. Okay, and if once I have this one-to-one function, once I have this injection, we know that this is only possible if the cardinality of N0 is less equal to N. That was the definition. Okay, and then by Cantor Bernstein, if you have A less equal to B and B less equal to A, that means their cardinalities are the same. Okay. So let's prove it. Well, I'm just going to give you the function. Okay, f of x is equal to x plus 1. So is this a valid function? Well, it's perfectly well defined for every element of N0. You just add 1. Okay. And when you add 1, do you get an element of N? Yes, because the smallest, you get all the natural numbers. The smallest you can get is 0 plus 1, which is in N. Okay, so it's a well-defined function. Well-defined. Now I'm going to show you how to prove that it's an injection. So we need to prove that f of x is 1 to 1. Okay, so that's all we need to prove. It's a well-defined function. We need to prove that it's an injection, that it's 1 to 1. And I'm going to illustrate how we typically make such proofs. So let me sort of make sure I don't erase that. Okay, so we prove such things. We prove that a function is an injection typically by contradiction. By contradiction.
So let's assume it's not an injection. So assume f of x is not 1 to 1. Okay. And now, what does that mean? So this is how the proof by contradiction goes. What does it mean that f of x is not 1 to 1? Well, if it's not 1 to 1, it means there are two different elements, x and y, which both map to the same number. Okay. It means that x, which is not equal to y, maps to the same value. What does that mean? That means that f of x equals f of y. Okay. Now, you use the fact that f of x equals f of y to get a contradiction. What does f of x equals f of y mean? It means that x plus 1, f of x is x plus 1, x plus 1 is equal. So this means x plus 1 is equal to f of y, which is y plus 1. Subtract 1 from both sides. This means that x equals y. Anyone see the contradiction? Yep. Because, the fact that f of x is not 1 to 1 means that there is this x not equal to y, for which f of x equals f of y. And now we just showed that x equals y. X not equals to y, x equals y. Very fishy. Fishy. And that's the end of the proof. That means that f of x is 1 to 1. And so that's the end of the proof. That's the way a contradiction proof goes. Okay. And typically, if you need to show that something is an injection, some function is an injection, you have to prove it this way by contradiction. Assume it's not an injection. Okay. That means you have two values which map to the same value. Okay. And then use the fact that they map to the same value to derive a contradiction. And once you have the contradiction, the assumption that f of x is not 1 to 1 is false. Okay. So therefore you conclude that f of x is 1 to 1. So it is an injection. So there is a mapping that's an injection from n0 to n. It means that the cardinality of n0 is less equal to n. A disaster for intuition. We thought that the size of n0 was n plus 1. No, it's n. The cardinality of n0 is equal to n. So this is wrong. It's equal to n. Stunned. Okay. Now, let me show you pictorially what's going on. And very often we resort to the pictorial type of picture. Okay. So pictorially what's going on? Since the cardinalities are the same, I should be able to find a bijection. So pictorially what's going on? Here's n0, here is n. So n0 is 0, 1, 2, 3, 4, 5, 6, 7, and so on. N is, so this is n0, n 1, 2, 3, 4, 6, 7, 8, and so on. And my bijection x plus 1, my injection x plus 1 happens to also be a bijection. And we can illustrate that in this way. So these guys are paired together. And the funny thing is, even though I have, in theory, strictly one more element in n0, which is this 0, I never run out of the ability to make the pairs. So every n0 is paired with an n, and every n is paired with an n0. Okay. And so this is a bijection. Okay. So let's talk about the even numbers. We think the cardinality of the even numbers is half the cardinality of the natural numbers. Let me give you a bijection from the even numbers to the natural numbers. Okay. So even numbers map bijectively to the natural numbers. Okay. Here, 2, 4, 6, 8, 10, so on. This is the even numbers. The natural numbers 1, 2, 3, 4, 5, and so on. There's my pairing, my correspondence. And I'll never run out of even numbers. Even though it looks like I have twice as many natural numbers, I'll never run out of even numbers. And if I want to know what's this mapping is, okay, I'll give the mapping from n to e. So f of x equals 2x. This maps n to e bijectively. So it maps n to e bijectively. Okay. And check that it's a valid function. Well, certainly we can evaluate it for every element of n. Okay. It maps to an even number, so it maps to an element of e. And can any different elements map to the same number? No, because if you have different elements, then twice of the, if you have, for example, 3 and 5, then taking twice 3 gives you 6, and twice 5 gives you 10. So different numbers, when you multiply by 2, result in different even numbers. So that's an injection from n to e. And that immediately shows that n is less equal to e. Okay, and since e is a subset of n, there we go. It suffices to just demonstrate this bijection. And of course, if you're asked to prove, this demonstrates that they have the same cardinality, but if you're asked to prove, you have to construct the function and show that it is a bijection, which means injection in both directions. Okay. What about the integers, which look like twice the size of the natural numbers? Well, now we're starting to get the hint. Okay, so the size of the even numbers, the cardinality of the even numbers, this is wrong, equal to the cardinality of n. Now we might guess, intuition is out the window. Okay, even though it looks like, it looked like the even numbers was half the size, and it looks like the natural numbers is about half the size of the integers. It doesn't, maybe we're wrong again. Maybe now we'll guess that, okay, they have the same cardinality. And indeed, they do. Let me give you the bijection. So let me do it in blue. The integers map bijectively to the natural numbers. Okay, and here is how. So here are the natural numbers. So the natural numbers are 1, 2, 3, 4, 5, 6, 7, 8, and so on. Okay. And I'm going to put the non-negative integers up on top. Let's say 0, 1, excuse me, 0, 1, 3, 1, 2, 3, 4, and so on. And I'll put the negative integers on the bottom. So -1, -2, -3, -4, and so on. And here, 0 to 1 paired, 1 to 3 paired, 2 to 5 paired, 3 to 7 paired, 4 to 9 paired. So this would be 9. Okay, and let's look at the negative integers. -1 to 2, -2 to 4, -3 to 6, -4 to 8, and so on. Okay, so what am I doing here? I'm pairing all the non-negative integers with odd numbers. And the non-negative integers is basically n0. And we know that, n0 is basically having the same cardinality as n, which has the same cardinality as the even numbers, which also then has the same cardinality as the odd numbers. So I'm basically pairing the non-negative integers with odd numbers and the negative integers with even numbers. That's it. Okay. Now, I encourage you as an exercise to actually figure out the function. Figure out the function that is this bijection. What is the function f of x, f of z, let's say, f of z, which implements this bijection? Okay. And show that it's a bijection. Okay. F of z basically breaks into two cases. If z is positive, if z is non-negative, then f of z is equal to 2 times z minus 1. Okay. F of z is 2 times z plus 1, and if z is negative, then it's equal to minus 2 times z. Okay. So it breaks into two cases, f of z. But you can construct this function and then prove that it's a bijection. I'm not going to go through all those details. We went through those details for n0. I want to get to the rational numbers because that's the interesting guy. It looks like the size of the cardinality of the rational numbers is a huge number, infinity times a huge number, infinity. We might expect that the cardinality of the rational numbers is much bigger than the cardinality of the natural numbers. There are way more rational numbers than natural numbers. And one way to sort of try to make sense of that intuition is to say, between any two rational numbers, there are not just one, but infinitely many other rational numbers. And that's not the case between any two natural numbers. Between any two natural numbers, for example, 7 and 10, there are only a finite number of other natural numbers. Between two consecutive natural numbers, there aren't any other natural numbers. So it looks like the natural numbers are sparse, okay, but the rational numbers are dense. Okay. Well, Cantor thought about this for a long time, okay, and eventually he managed to show something very stunning. What he managed to show was that the cardinality of the rational numbers, which looks much, much larger than the natural numbers, is actually the cardinality of the natural numbers. Okay, now we had better think about this. How can this be? Okay. Rational numbers is integers over natural numbers, and the rational numbers are dense on the real line. The natural numbers are sparse, and the size, the number of rational numbers, there aren't more rational numbers than natural numbers? Nope. Okay, and Cantor found a bijection. Okay. Now, it's going to be a little bit easier for us to show that bijection using a different method, which we call the list method. Okay, so we're going to erase, and I'm going to show you the list method. And this is usually the method for showing that some set is countable. It's sort of an informal way to show that it's countable. The formal way is, of course, to show that there's an injection from Q to the natural numbers. But I'm going to show you what an injection looks like, okay? And, summarize it in what's called the list method. And the list method is very powerful for showing that a set is countable. Okay, so let's erase. The informal way to show that a set is countable is to show that it can be listed or ordered. Okay, so we'll call this the list method. The list method. Okay, so let me tell you exactly what that means. It's a much easier way to show that something is countable. Okay, although formally speaking, you can still always resort to the injection approach. Okay, so A is countable. Okay, so what does that mean? It means that the cardinality of A is thus equal to the cardinality of the natural numbers. And what that means is that formally, it means that A is injectively, can be injectively mapped to the natural numbers. Okay. Now, it turns out that this is equivalent to this informal sort of notion that A can be listed, can be ordered. A can be listed / ordered. Okay, so here we have a sort of an example of a typical set A and what an injection to the natural numbers might look like. Okay, so let's see how we can order these elements, how we can list them. Okay, so I'm going to order the elements. Okay, and how would I order the elements? Well, what I can do is I can say, well, we're mapping this set A to the natural numbers. It means that it means that a subset of the natural numbers will be used, and any subset of the natural numbers by the well-ordering principle has a minimum. And look, in this case, the minimum is 2. Okay, so what element maps to 2? The first natural number that's used, the square. Okay, so I can take the 2. Okay, and I'll call the first element of A the square, which maps to the smallest natural number. Okay, and then I can go along the natural numbers and see which natural numbers are used. And as the natural numbers are used, I can spit out the elements of A as a list, as an ordering. Okay, so the next natural number that's used is 3, and so that gives me circle. And then I don't use 4, I use 5, and that gives me diagonal. And then I use 6, that gives me this weird arrow. And then I use 7, that gives me S. And then I don't use 8, I use 9, that gives me the box with a check. Okay, and then I use 10 and 11 $. And so on. Okay, so as the elements in the natural numbers are used, so I can output an ordering, a list of A. Okay, and if I wanted to, I could call this A1, A2, the first that was output, the second, A3, A4, A5, and so on. And by the well-ordering principle, we know that this is possible. And if I wanted to, this mapping now also implicitly defines an injection to the natural numbers. So square maps to 1, first element. Circle maps to 2, second element. Okay. And so here's another injection to the natural numbers. And so, that's what a list means. That's what an ordering means. You put A with a first, a second, a third, a fourth, a fifth, and so on. Okay? And so let's see this list method in action. So let me show you now lists for all of these sets. We're going to postpone Q for the moment. Q is a little more complicated. So the list method in action. So just show me a list. Okay? Okay, so N0 already exists as a list. First, second, third, fourth, fifth. Naturally listed. Okay. Even numbers already exists as a list. Second, fourth, first, second, third, fourth, and so on. Okay. Now, the integers. Okay. Well, how would we list them? So now I'm going to show you an example of what is not a list. So not a list for the integers. Okay, so I could try to list the integers as follows: 0, +1, +2, +3, and so on. -1, -2, -3, okay, and so on. Yeah, that's not a list. Now, at a high level, the way you can diagnose that this is not a valid list at a high level is we are using the ... twice. Okay. It's a bit of a shallow way to diagnose it, but that's a sign that this is not a valid list. So in all the valid lists, the ... should make the pattern obvious and be used once. Now, formally, what does that mean? That means that 1. Okay. Every element of your set must be in the list. Every element of your set must be in the list. Okay? In this case, if you think of this as a list, well, it's clear that every element of Z is in the list. But now it's going to violate the second property. The second property is for any arbitrary element of your set, for any element of your set, you should be able to compute the list position, okay, without any problems. Okay, you should be able to unambiguously assign a list position to any element in your set. So, what's the list position of -3? Okay, well, where does the list begin? Does the list begin at -infinity here? In which case, the list position of -3 it's not well defined. So this is not a good list. Okay, so if you can check these two conditions, you have a good list. You have a valid list. So let me give you a valid list for Z. So a valid list for Z is 0, +1, -1, +2, -2, +3, -3, +4, -4. Okay, and so on. That's a valid list. Well, at a superficial level, we use ... only once. But now let's check. Is every element of Z in this set? Let's say, for example, +5. Is +5 in this set? Yes, it will eventually be reached. You can just look at this pattern. Okay, plus or minus any integer will eventually pop up. So any integer is in this list. Can we compute the list position of any number? So for example, what is the list position of +5? Okay, we can compute it. It's 1, 2, 3, 4, 5, 6, 7, 8, 9. The next is +5, 10. So the list position of +5 is 10th. Okay, and I urge you as an exercise, compute for an arbitrary Z in my integers, compute a formula for the list position of Z. And you find a formula for the list position of Z. It's not too hard, but sit down and convince yourself that you can do it. Then we have a valid list. Okay, so this is a valid list for the integers. It's countable. Anytime you can list a set, it's countable. Its size is at most the size of the natural numbers. And intuitively, you can think of this as follows. The natural numbers are 1, 2, 3, 4, 5. You can think of that as first, second, third, fourth, fifth, sixth, and so on. So anytime you can place a set in an order where there's the first, the second, the third, the fourth, the fifth, the sixth, and so on, then it is in correspondence with the natural numbers, and so they basically have the same size. Okay, or the set you have, which with the first, second, third, and so on, is at most the size of the natural numbers. Okay, so you can think of the natural numbers as a natural way in which we index lists, in which we order the elements of a set. Okay, first, second, third, and so on. Okay. Let's prove a theorem, since it's a math course. Theorem. If you have two countable sets, the union is countable. The union of two countable sets is countable. So, if A is countable, so this means that A can be listed. So A is a list, A1, A2, and so on. And B is countable. So B is a list, B1, B2, and so on. Okay. This means that the union is countable. A union B is countable. That means that there's a list for A union B. For A union B. Proof. Let's give you the list. Trivial. Proof. A union B is equal to the following list. A1, A2, A3, and so on. B1, B2, B3, and so on. Pause the video for a couple of seconds. Are you satisfied with this proof? Okay, I'll give you a few seconds. 1, 2, 3, 4, 5. Okay, you came back and said, at a superficial level, this is not a valid list because look, you're using ... twice. You're right, it's not a valid list. Now, how do we formally diagnose that this is not a valid list? Let's ask the following question. What is the list position of B1? What is the list position of B1? Well, when you think about it, you'll have a lot of difficulty figuring out what the list position is of B1. Because, well, first, second, third, fourth, fifth, sixth, and this could be infinite. A could be infinite. So the A's are going to use up all the list positions. So I cannot tell you what the list position of B1 is, and that fails my second condition, that for any element in the union, I should be able to tell you what its list position is. Okay. So this is not a valid list, but there's an easy fix. I'll give you a valid list. So here is a valid list. A union B is equal to A1, B1, A2, B2, A3, B3, and so on. Okay. Interleave the lists of A and B. Start with A, then B, then A, then B, then A, then B, then A, then B, and so on. This list is valid. At least on a superficial level, we can demonstrate the pattern with one ... But now, you should be able to compute the list position of any A or any B. For example, what's the list position of AI? Okay, so look at where the A's are. They're at the odd positions, 1, 3, 5, and so on. So the list position of AI is 2i minus 1. What's the list position of BI? It's just 2i. There. So you give me any member of the union, I have, without any problem, computed the list position, I have a valid list. Is every element of B in here? Well, yes, every element of B is in here. So no two elements of B have the same list position, no two elements of A have the same list position, and elements of A and B don't have the same list position. Okay. So one thing I forgot to mention, that your list cannot give the same list position to multiple elements. That's what it means to list them. Okay. Different elements appear at different spots in the list. Okay. So that's the list method. Okay. We're going to use the list method to show that the rational numbers are countable. So we're going to demonstrate now a list for the rational numbers, and you might be thinking to yourself, how am I going to get a list for the rational numbers? Looks a bit tricky. Okay? So let's erase and show, using the list method, that the rational numbers are countable. So, Cantor was looking for a set that was bigger than the natural numbers. So, and he really thought that the rationals was that set. And so he spent a lot of time trying to prove that there's no injective mapping from the rational numbers to the natural numbers. And then he figured out a way to list the rational numbers. And that was a devastating blow, because that proved that the rational numbers are listable. And if they're listable, they're countable. Okay, so let me show you how he listed the rational numbers. So Q, the rational numbers, are ratios of integers and natural numbers. So let me list the natural numbers. We know the natural numbers are listable by definition. So the natural numbers are 1, 2, 3, 4, 5, 6, 7, and so on. Okay, and now let me list the integers. And how do we know the integers are listable? I just gave you that list. The integers are countable. So 0 plus 1 minus 1 plus 2 minus 2 plus 3 minus 3. Okay. So and we can keep going in this list. Okay. Now every ratio of an integer, so this is the integers. So every ratio of an integer with a natural number is a rational number. So in this case, you'd have 0 over 1, plus 1 over 1, minus 1 over 1, plus 2 over 1, minus 2 over 1, plus 3 over 1, and so on. Okay, 0 over 2, 0 over 3, 0 over 4, 0 over 5, okay, plus 1 over 2, plus 1 over 3, plus 1 over 4, plus 1 over 5, and so on, and so on. Minus 1 over 2, minus 1 over 3, minus 1 over 4, minus 1 over 5, and so on. Plus 2 over 2, plus 2 over 3, plus 2 over 4, plus 2 over 5, minus 2 over 2, minus 2 over 3, minus 2 over 4, minus 2 over 5, and so on. We can go on filling in this table. So this table contains all the rational numbers. Now notice that the values in this table are not all different. So all these are 0. So the rational values are much less than the rational numbers as defined as a ratio of an integer with a natural. Okay, that's fine. If I show that this big set is even larger than the rational values, the distinct values in this set. Okay, but now here's how Cantor listed them, and let me show you. Okay, this very interesting way to list. So let's start here. Okay, so we have to start somewhere. If we're building a list, let's start somewhere. Okay, so we start here, and I'm going to snake through. See? And so on. Okay, so you see, I'm creating a path that goes through all these rational numbers. Okay, and it'll go up and come down, go up, and so on. Okay. Now, it may not be immediately obvious to you, but it should be reasonably obvious that any particular rational number will eventually be reached by this list. So I'm going to output now my rational numbers in the order that they are traversed by this list. So here's my list of the rational numbers. Q is equal to 0 over 1, 1 plus 1 over 1, plus 1 over 2, 0 over 2, 0 over 3, plus 1 over 3, minus 1 over 3. Okay, so I went this, then minus 1 over 2, minus 1 over 1, minus 1 over 2, minus 1 over 1, then plus 2 over 1, plus 2 over 1, and so on. Okay, so here, spit out. As you traverse this list, you spit out the numbers. You've got a list of the rational numbers. Challenge. If I give you a rational number, so if I give you z and n, so my rational number is z over n. Find a function, figure out where is this z over n, where is this rational number in my list? What is the list position? What is the list position of the rational defined by z n? So that's a challenge exercise for you. It's not that trivial, but it's also not impossible. You can figure out a formula for the list position of z n. Okay, and so that means that every rational number is in this list, and you can construct the list position given the rational number. Rational numbers are countable. Finite binary strings. Finite binary strings. Now we are getting closer to home. Finite binary strings, and I'll tell you why in a minute. But let me list the set of finite binary strings, and I emphasize the word list. And the moment I can list it, the finite binary strings, it means it's countable. So the finite binary strings, B, okay, is equal to the set. Well, we have the empty string. Okay, then we have 0, 1. Then we have 0, 0, 0, 1, 1, 0, 1, 1. Okay, then we have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. 0, 0, 0, 0, and so on. Okay. I've chosen to list the binary strings, the finite binary strings, in a particular order. So I'm starting with the shortest, and then gradually increasing the length. And within a particular length, I list them in order of increasing value. So this value is 0, then 1, then 2, then 3. 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay. 0, 1. Oh, I left one out here. I left out 0, 0, 1. Okay, so now I have, I have it here. Okay, 0, 1, 2, 3, 0, 1, 2, 3, 4, 5, 6, 7. Okay, so those are the 8 length 3 binary strings. Okay, so interesting challenge. Given a binary string, B1, B2, B3, up to BK, we can compute its value in the standard binary way. Show that the list position is equal to 2 to the length of the string, 2 to the length plus the value of B1, B2, up to B2. So I'm claiming that this is a formula for the list position of any given binary string. Okay, so prove it. Okay, and it's proved in the text. Okay, but it's a good exercise for you. But once I give you an unambiguous way to compute the list position of any string, okay, then and the list position of two different strings are different, then that means that I have a valid list. And so I've listed the finite binary strings, and so the finite binary strings are countable. Okay. They have a size, a cardinality, which is at most the cardinality of the natural numbers. Why do we care about finite binary strings? Okay. So, computer programs. A computer program. So you write your computer programs in whatever fancy language you want, C++, Java, Python, whatever. At the end of the day, this fancy program has to be converted to a bit string so that it can be represented to your, CPU. Okay. So every computer program is a finite binary string. It's a finite string of bits. Okay. So every computer program is a finite binary string. Now, not all finite binary strings are valid computer programs, but in principle, it could be treated as a computer program, any finite binary string, but it just doesn't do anything. It just doesn't work. Okay? So, but the valid computer programs, are a subset of the finite binary strings. And so that means that the size, the cardinality of the valid computer program is at most the cardinality of the finite binary strings, which is at most the cardinality of the natural numbers. Okay. Okay, it turns out that the cardinality of the finite binary string equals, because you can also get an injection from the natural numbers to the finite binary strings. So here's the first, second, third, fourth, fifth, sixth, seventh, and so on. We can index, we can order, we can list the finite binary strings. What does that mean? That means that we can index, we can order, we can list the valid computer programs. Okay, do we care? Yes, we care. Okay, but we'll see why later. So, Cantor is looking at the state of affairs, and it looks like everything has the same cardinality of the natural numbers. He's really trying to find something. He's really trying to find out whether there's any set whatsoever, okay, which has a cardinality which is larger than the natural numbers. Okay, and he's starting to lose hope because he thought that rationals would do it. They didn't do it. All possible finite binary strings doesn't do it. Is there any set which is larger than the natural numbers? And after some time, he finally found one. Okay, is the real numbers. And he gave a proof that's so beautiful, it's a definite contender for the most beautiful proof ever. Okay. Now, related to the real numbers are the infinite binary strings. Okay, so let me show you that relationship at a very sort of high level without getting into the details. Okay, so this is the finite binary strings. Let's look at a real number x. Okay, so x can be represented, and let's look at the real numbers between 0 and 1, just for simplicity. So x has a binary expansion, okay, as a decimal. So it could be represented as, for example, 0.0011, 0.001001, and so on, right? So you could have a binary expansion, which could in principle never end. If it ends at some point, you can just add zeros to the end. So any real number has an infinite binary expansion as a decimal, as a binary equivalent of a decimal. Okay. And so what's on the right of the decimal point here is exactly an infinite binary string. And so the real numbers are in some sense in correspondence to infinite binary strings. You can think, if you're more familiar, a real number has a decimal expansion. So a decimal expansion is an infinite decimal string. Well, binary decimal, we can always convert between the two. So infinite binary strings are definitely related to real numbers. Okay. Cantor showed that the real numbers are strictly more numerous than the natural numbers. So he finally found a set that's bigger than the natural numbers. A beautiful proof he gave. Now, we're not going to consider the real numbers. It's a little bit more complicated with the real numbers, and you can see the text for that. We're going to consider another set which is just as useful for us, which is the infinite binary strings. And so there's this relationship which suggests that the real numbers will also be strictly larger than the natural numbers. We're going to show that the set of infinite binary strings, okay, is not countable. Cantor's theorem. I'll call it Cantor's theorem. Although there's another theorem named after Cantor. That's how many things he did. So I'll call it, I'll say due to Cantor. Okay. Infinite binary strings are not countable. So if I define B infinity as the infinite binary strings, note that none of the strings in this set are infinite. B infinity is strictly all the infinite binary strings. So B infinity is not countable. So this means that the cardinality of B infinity is greater than the cardinality of the integers. Of the natural numbers. Okay. And so I'm going to erase this, and I'm going to show you the beautiful proof of this. It's a proof by contradiction. Fantastic proof. Okay. Let me just remind you what we have to show. What do we have to show? We have to show that in order to show this, we have to show that there is no injection. There is no one-to-one mapping from B infinity to the natural numbers. Okay. That's what makes it hard to show. That's why he struggled so much, okay, in order to find a set that he could prove is not countable. Yes, you have to show. So you want to show that the cardinality of the infinite binary strings is strictly larger than the cardinality of the natural numbers. So you have to show that no matter how you construct a one-to-one mapping, it will not be a valid one-to-one mapping from the infinite binary strings to the natural numbers. It's not possible to do. Okay. And so, the method of proof that he basically invented in order to prove this is what's called Cantor's diagonalization argument. So, Cantor Proof. Okay. And we call this Cantor diagonalization. Okay. And it's a little bit of a subtle proof, but it's not a hard proof. It's a subtle proof. So, it's a proof by contradiction. Proof by contradiction. Okay, so suppose the set of infinite binary strings is countable. B infinity is countable. Okay, that means you can list it. So B infinity is equal to a list of infinite binary strings. Let's call the strings, S1, S2, S3, S4, and so on. Okay, that's the list method. You can list it. Okay. This implicitly defines the injection. Okay. And if you have an injection, then you can use that injection as we showed earlier to construct this list. Okay. So what Cantor said is, okay, so let's have a look at what this list looks like. So you've got S1, S2, S3, S4, S5, and so on. Okay. So each of the strings that you have listed, we cannot actually list them, okay? But because they're infinite binary strings. But let me just, imagine that I could have written them down. So this string looks something like maybe 0, 1, 1, 1, 0, 1, 1. Okay. So it's got a first bit, a second bit, a third bit, a fourth bit, a fifth bit, 6, 7, maybe 0, and it goes on forever. So now what I'll do is I'll draw some columns to identify the various bits. Okay. Here are some columns to identify the various bits. Okay, so what does this second string look like? I don't know. Let's just imagine 110111110 dot dot dot. Okay, they're all different strings. They're all different binary strings, infinite binary strings. I cannot list any one of them, but I'm just pretending like I could. Okay, 0000110 and so on. 11100111100 and so on. Okay, 001101110 and so on. Okay, so here's what Cantor did, and this is why it's called Canto Diagonalization. Okay, so let me now tell you about this. These are the strings. And what he said was, let's consider the diagonal of this table. So the bit in position 1, 1. Okay, so let's consider this guy, all the diagonal bits, and so on. Okay, so since this is a list of this is an infinite list. Okay, this diagonal list of diagonals is also going to be an infinite binary string. Let me call that infinite binary string B. Okay, so B is equal to 0, 1, 0, 0, 0, and so on. In this example, 0, 1, 0, 0, 0, and so on. Okay. Well, since this is a list of all the strings, remember the two conditions for your list. Any string must appear in here, and it also must have a list position. Okay, so this guy has a list position. This guy appears in the list. Okay, good, no problem. But that's not the crux of the argument. Here comes Cantor's deadly blow. He says, okay, so you've constructed this diagonal string of bits. Let's construct the complement string. So wherever there's a 0, take a 1. And wherever there's a 1, take a 0. Okay, so let's construct B bar, which is 1, 0, 1, 1, 1, and so on. Okay, so you take the opposite. You flip the bits in the string B. Now, just like B must appear somewhere, B bar must appear somewhere. Must appear in the list. Okay. Now the question becomes, but where? Okay. So let's say it appears in the kth position. In the kth position. Okay. So now we have to look at the k. Let's look at the kth bit in B. So if it appears in the kth position, for example, let's take as an example, it appears in the third position. Third position. Okay. Well, the third bit in B, so 1, 2, 3, the third bit in B is exactly the third bit of the string that appears in the third position. Okay. The third bit in B is exactly the third bit that appears, exactly the third bit of the string in the third position. And the fourth bit in B is the fourth bit in the fourth string. And the fifth bit in B is the fifth bit in the fifth string. Okay. So now let's say B bar is appearing in the third position. Let's look at the third bit of B. It matches the third bit of that string. So that means that the third bit of B bar is the opposite. So B bar cannot be the third position. Can it be in any position? Let's say the kth position. In the kth position, the kth bit of the string in the kth position matches the kth bit of B, which is the opposite of the kth bit of B bar. So the kth bit of B bar mismatches with the kth bit of the string in the kth position. So, and that argument works for any k. So this guy B bar cannot be any of these strings. Okay? And so that means that this list is incomplete. The list is incomplete. And that's a contradiction because it was supposed to be a valid list, which means it contains all the strings in B infinity. So that's the starting position. This list contains, we start with the assumption that B infinity is countable, and so it's listable, and this list contains all strings in B infinity. And now we've just found a string in B infinity that it does not contain. And that's a contradiction. That's a contradiction. Fishy. And that's the end of the proof. That means that, B infinity cannot be countable. If it cannot be countable, if it's not countable, it means it cannot be listed. If it cannot be listed, there's no injection from b infinity to n. And so the cardinality of b infinity is strictly bigger than n. Wow, we have found a set that is bigger than n. And then Cantor went on to find, he called the natural numbers the first level of infinity, aleph naught. Okay, and he called this b infinity the cardinality of the continuum, okay, little c. And he went on to define a whole hierarchy of infinities. Okay. But we're not going to be so concerned with that. And that hierarchy of infinities is called Cantor's paradise. So it must be beautiful. Okay. You can read about it in the text. But we are done from the perspective of what we need for the theory of computing. Because now I'm ready to deal a deadly blow to the theory of computing. And so whatever we do from here onwards is going to have to take into account this deadly blow. Okay, so what's the deadly blow? So I'm going to erase the proof, Cantor's beautiful diagonalization proof. Okay. And now we're going to show you how infinity is going to come and bite us. Okay. So let's talk about computing. Okay, so Cantor came before Turing. Turing came later. Okay, and in Turing's time, he's interested in building a theory of computing. Well, okay, so what do we like to compute? Let's talk about the simplest thing that we might like to compute. Okay. A binary function. So a function, so can we compute functions from, the natural numbers to the binary numbers. So this is a binary function. So you can think of the function f of n. Okay, it takes as input a natural number n, okay, and outputs either 0 or 1. So it's a binary function. Let's look at what such a binary function looks like. So if I list my natural numbers, 1, 2, 3, 4, 5, 6, 7, 8, and so on. Okay, and now I can compute f of n. So f of n, f of 1, what is it? Maybe 1. What is f of 2? Maybe 0. What is f of 3? Maybe 7. Oh, sorry, it's a binary function. Maybe 1, 1, 0, 0, 1, 1, and so on. So what this says is f of 8 is 1. Okay? So in order to specify a binary function, I need to tell you what does it compute, what does it evaluate to for all the natural numbers. In other words, I need to tell you an infinite binary string. Okay? So all possible binary functions, okay, corresponds to all possible infinite binary strings. And now this should remind you of the quote I mentioned at the beginning of the class, Stephen Klein's quote, that a function or a program, okay, or an algorithm is a finite answer to infinitely many questions. Okay, so what do we mean by an algorithm? We would like to write a program to compute f of n. So write a program to compute f of n. Okay. So now we have written a program and it gives us the answer to infinitely many questions. F of 1, what is it? F of 2, f of 3, and so on. So, we could say that a function f of n is computable if we can write a program to compute, i.e. output f of n. When it gets the input n, it outputs f of n. Okay. So, yeah, well, we're familiar with this. We can write a program to compute n squared. We can write a program to compute e to the power n. We can write so many programs to compute so many complex things. Okay. But now comes the deadly blow. Okay. How many possible functions are there? Every infinite binary string gives me a possible function. So the number or the cardinality of binary functions is basically equal to the cardinality of B infinity, because, every binary function is given by an infinite binary string, and every infinite binary string specifies a binary function. So that's a bijection between binary functions and infinite binary strings. Okay? But we just argued that computer programs are finite binary strings. So computer programs, the cardinality of computer programs is at most the cardinality of the finite binary string, because any computer program is a finite binary string. Finite binary strings, and we know we proved that this is countable. We gave a list, so this is at most the natural numbers. Does anyone see a problem here? I'll give you a couple of seconds. 1, 2, 3, 4, 5. Okay, if you're coming back, let me tell you what the problem is. The number, the cardinality, the set of binary functions that we might like to compute, and these are just the binary functions. Forget about all kinds of things that we'd like to compute. Now, the binary functions that we might like to compute, okay, is a set which is strictly larger than the countable natural numbers, which is, larger than or equal to the number of programs we have. So now if we think intuitively in terms of numbers, the number of binary functions we would like to compute is much, 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 much larger than the number of computer programs that are even possible. Forget about the valid programs. Forget about the programs that compute binary functions. The number of possible computer programs is much, much smaller. It has the cardinality of the natural numbers, which we just proved is strictly less than the cardinality of the infinite binary string, which is the binary function. So, conclusion. Number of computer programs is strictly less than, because this is is strictly less than the number of binary functions. And this is just binary functions. Well, that is the punchline of today's lecture. This is why infinity came into the whole discussion. What is this saying? If there are way fewer programs than functions, and these are just baby functions, if there are way fewer programs than functions, it means there are many functions for which there are no programs that can compute those functions. It's not that there are many functions for which we don't know how to write the program. There just are many functions for which there do not exist computer programs that compute that function. There are many things that we cannot compute. So the conclusion. There are many things we cannot compute. Wow! And it's the theory of infinity that tells us that. It's the theory that was laid forth by Cantor that tells us that. Computer programs are far less numerous than things we might like to compute. For example, binary functions. A function that takes as input any natural number. And so this is the problem. This is the situation we face when we try to develop a theory of computing, a theory of an algorithm being a finite answer, a finite binary string to infinitely many questions. Okay. It poses a real challenge because it means there are several functions we cannot compute. So we need to figure out what those are so that we don't waste our time on those, and figure out what we can compute. So we need to understand. So now we have, I don't mean to do this, but I have to do this. I'm going to shatter your dreams. You cannot compute everything. There are things you cannot compute. And so that's what we're going to study. What can we compute and what can we not compute? And the theory of infinity plays a central role in that discussion. Okay, until next time, checking out.